So learning about periodic trends is great because you can make some predictions about how things will behave. Okay, so let's look at this atomic radius. And we will consider both as you go across a period. And we will also look at down a group. Okay, what did we just see? We saw with our carbon going to nitrogen, it got smaller, right? Okay, so as we go across a period, the radius, it decreases. It gets smaller and smaller and smaller. That is always due to the increasing effective nuclear charge. Okay. I wonder if I have numbers handy. Let me see. Get a few little page turns here. Radius. I do. Okay. So, lithium is 152 picometers. Picometer. Pico 10 to the minus 12th meter. It's a little tiny lithium. Okay, but if we look at, I'll have this somewhat handy right here. Okay, right next to lithium, we've got beryllium. So beryllium, as you can see, it's a little bit heavier, more massive. It's got an additional proton. And we have now learned a little bit about effective nuclear charge. So because we would now expect beryllium, those outer electrons, to experience an increased effective nuclear charge, increased feeling that the charge in the nucleus, we would expect its overall atomic radius to shrink. And what is that number? Yes, 112. Picometers. Okay, so I always like to see the actual evidence of this. All right, not just necessarily hearing about the trend, but actually getting some data, some things that have been measured by people. I find that helpful. Let's see, a couple other examples. Boron is our next element, element 5. Okay. And boron has a radius of 83. Okay, so hopefully you are seeing this trend. I will add carbon in here. 77. Now, where this gets fun is period 2 actually has an anomaly. Okay, so learning about periodic trends is great because you can make some predictions about how things will behave. All right? But trends are just that. They are trends. They are not always super specific. They will not always be followed exactly. And that same is true for period 2 on the periodic table with atomic radius. And we're about to see that right now, and I'm going to tell you exactly why this is an anomaly. Okay, so we've got lithium, beryllium, boron, carbon. Next is nitrogen. Nitrogen is 70 picometers. And then we have oxygen. Check it out. Okay, so we've seen it get smaller, smaller, smaller. Now, the jumps in terms of how much smaller they're getting, notice something with that. 152 down to 112. That radius went down by 40 picometers. Then we go from 112 to 83. That goes down by 30 picometers. Then 83 to 77, that's only 6. And 77 to 70, that's only 7. So once you get as small as boron, you have much smaller changes in what's happening. And now look at this oxygen. It actually goes up. That radius increases ever so slightly. It's 73, so it's not a lot bigger, but it's bigger. And the fluorine atom is trying to continue the trend. It gets a little bit smaller than oxygen, but not very much. It's 72. Okay. So we're seeing this trend is fine, it's fine, it's fine. And then here's our glitch. Okay, right when we hit oxygen. Why is this? Okay. Well, essentially what we're doing is we are cramming, literally we're cramming more and more electrons into a very small volume. And with oxygen, we come to a point where we actually have to pair up 2 of the electrons for the first time as we get into this region here in an orbital. And if you haven't learned about orbitals yet, that's okay. The main thing to remember here is that we have a lot of electrons in a confined space, and this is where they just need to repel, they do repel each other enough that the radius actually puffs out a little bit to make room for these electrons that are repelling each other. Once again, with fluorine, we've got additional effective nuclear charge. Those electrons are absolutely being attracted significantly to the nucleus, but we're cramming in a lot of negatively charged electrons into a very small volume. So they can't get any closer together than really where it's maximized is at nitrogen with 70 picometers. They just can't get smaller than that. Okay, so this is an anomaly, but it is explicable. And if we go down to the next period, okay, period 3, where we have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, this period does follow the expected trend. The radii go down, 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 down. Okay. So it is truly just happening in group 2 because of this small volume of those. But I did want to point this out because it's a thing, and These are really common elements, especially in organic chemistry. Organic chemistry is based on carbon, and a lot of organic molecules have nitrogen in them, have oxygen. Some of them have fluorine as well. So they're common, and I want you to know about that anomaly that's there. Okay. What about down a group? Okay. So now we have a different situation where we are considering, and we can just look at hydrogen versus helium. Sorry, not helium. Hydrogen versus lithium, sodium, potassium, rubidium, etc. And what's happening here is that with each element in this group, there has been a complete shell of electrons added. So hydrogen, helium, lithium. So lithium has that inner shell, and then with just one electron in the valence shell. Sodium, it's got two of those inner shells with one electron in the outer shell. Potassium, it's got three inner shells. Okay, so you're getting the idea here. And so essentially, in fact, if I think I have lithium is listed here. So why don't we just list sodium and potassium underneath here so we can follow our trend down as well. Lithium, the radius is 152 picometers, and sodium is 186. Okay, so this is getting larger because we are adding a whole nother shell of electrons. Potassium. We are adding a whole nother shell of electrons. It's going to be bigger. 227 picometers. Okay, so down a group, we will always see that the radius gets larger. No exceptions. Radius increases. Okay, and this is due to the fact that we are always adding a whole nother shell of electrons. Due to increased electron shells, which means increased distance. Okay, so every time we are adding another shell, we have this kind of situation, kind of like a bullseye, right? Where a bullseye is in the center, and as you create each additional ring, rings of an onion is another analogy here, and as there's another ring, we are getting further and further away from the nucleus, and we are increasing this distance as we keep going from here to here, here to here, here to here, increasing the distance. Lithium, sodium, potassium, essentially. I'm going to put this on here. No exceptions. I love it when there's no exceptions to certain rules or observations. It just makes it so much easier. Okay. All right, so there's our atomic radius trend.